Hello, my name is Sarah Alec. I am a PhD student under Dr. Brian Wong at the University of California, Riverside. I am pleased to present a recent study by Dr. Brian Wong and myself, Inconsistencies in the Electronic Properties of Phosphorene Nanotubes, New Insights from Large-Scale DFT Calculations. Since its isolation in 2004, graphene has become one of the most promising materials of the past decade, particularly for electronics. However, the lack of an intrinsic band gap in graphene inhibits its use in modern electronic devices, sparking a search for other 2D materials with desirable properties. One of the most promising candidates is phosphorene, a single monolayer of black phosphorus arranged in a puckered honeycomb structure. Due to its anisotropy, we expect that wrapping phosphorene into nanotubes, hereafter referred to as PNTs, should result in unique tunable electronic properties. However, the results to date are conflicting, with one study by Guan et al. Claiming that PNTs exhibit primarily indirect band gaps, and another study by Guo et al. Claiming that PNTs have only direct band gaps. To shed light and bring closure to these conflicting results, we present a thorough analysis of the electronic properties of these PNTs using large-scale density functional theory calculations in conjunction with large TZVP all-electron basis sets. While we present only results from the B3 lip functional, we also performed calculations with the range-separated HSE6 and the pure semi-local PBE functionals to verify that our findings were not due to our specific choice of exchange correlation potential. In this study, we considered two PNT chiralities shown here, armchair, or 0M, and zigzag, N0. In contrast to both of the previous studies, we find that all PNTs exhibit both indirect and direct band gaps. As expected, the band structures of large diameter PNTs approach the infinite limit of the phosphorene sheet, with a direct band gap at the gamma point. Interestingly, however, we find that below a certain size threshold, 0.8 and 46.0, for armchair PNTs and zigzag PNTs respectively, all PNTs exhibit an indirect band gap. A natural question then arises. What is the underlying electronic mechanism that causes this direct to indirect transition? To explore this question, we note that wrapping the phosphorene sheet into zigzag PNTs and armchair PNTs is analogous to stretching the sheet in the zigzag and armchair directions respectively. In a recent study, Peng et al. Showed that stretching phosphorene in either direction causes band gap transitions similar to the transition we observe in the PNTs. As demonstrated by Peng et al. And by our own calculations shown here, stretching causes a shift in the conduction band minimum, or CBM, away from the gamma point. In particular, for each direction, the CBM shifts in the symmetry direction of the corresponding nanotube. Namely, stretching the sheet in the zigzag direction causes the CBM to shift toward the Y point, and stretching in the armchair direction causes the CBM to shift toward the X point. This transition occurs because as the sheet is stretched, there is a competition in energetic stability between the orbital at the new CBM and the orbital at the old CBM at the gamma point. Following a similar analysis to Peng et al. For the sheet, we plot the CBM for the PNTs immediately before and after the transition. In the armchair PNTs, decreasing the nanotube size stabilizes, or decreases the energy of, both orbitals at A7 and A8. But the orbital at A7 stabilizes at a faster rate. As shown below, A8 is non-bonding around the circumference, while A7 is anti-bonding around the circumference. Thus, increasing the strain has a much stronger stabilizing effect on A7 than that on A8. For the 07 armchair PNT, A7 is stabilized and becomes the CBM. In the zigzag PNTs, decreasing the nanotube size destabilizes or raises the energy of Z46, but stabilizes Z45. While both of these orbitals are bonding around the circumference, Z46 has stronger bonding character, i.e., higher orbital overlap in the outer ring and in the inner ring. However, Z45 is bonding only along the outer ring. Consequently, increasing the strain has a stronger destabilizing effect on Z46, leading to a shift in the CBM to Z45. To conclude, using large-scale DFT calculations and detailed orbital analyses, we have shown that all PNTs exhibit a direct to indirect bandgap transition. This newly discovered complexity allows a wider range of tunability than traditional carbon nanotubes. Our results have implications for applications requiring fast charge recombination, i.e. a direct bandgap, such as light-emitting and laser diodes, as well as applications requiring slow recombination, i.e. an indirect bandgap, such as solar cells. Lastly, we would like to acknowledge support from a NASA Miro Fields Fellowship and the National Science Foundation for the use of supercomputing resources. Finally, we would like to thank you for your interest in our work.